We've looked at the FAA approach chart for the VOR runway 10 approach at the Riverton, Wyoming Regional Airport. As an introduction to Jeppesen approach charts, let's look at flying that same VOR approach, but this time we'll use a Jeppesen chart. Both FAA and Jeppesen charts meet the FAA requirements for approach charts. The same information is shown, but with some differences in the presentation. The title indicates that a VOR receiver is needed to fly this procedure. The title of this approach indicates that both VOR and DME are required. The OR on this approach indicates that you may substitute a GPS for the VOR receiver. Having both types of navigation is not required. Jeppesen's briefing strip shows the communications frequencies across the top. Below that is the NAV8 ID and frequency for the approach, the final approach course, the minimum altitude at the final approach fix, the minimum descent altitude or decision altitude, and the airport and touchdown zone elevations. Below that is the missed approach procedure. Procedure notes and word on pilot-controlled lighting is below that. The minimum safe altitudes are shown on a box to the right of this information. The scale of the chart is shown to the left. In the profile view, Jeppesen shows the distance from pilot to the end of the runway and separately depicts the distance to the missed approach point. Inbound from the north on the airway leading to the Boysen Reservoir VOR DME and cleared for the VOR runway 10 approach, follow the approach transition to Riverton via the 180-degree bearing at a minimum of 7,700 feet. The distance to the Riverton VOR DME is 19.8 miles. Halfway between the VORs, change over to the Riverton VOR DME. As you cross the Riverton VOR DME, put into practice the 5 T's. They are time, turn, twist, throttle, and talk. The first T, time, is not necessary since the VOR is not the initial approach fix. Turn to a heading to intercept the approach course outbound. This turn is made to a heading which will intercept the 275-degree bearing. Intercepts are made at 30 or 45-degree angles. In most cases, the 45-degree intercept is preferred because the outbound course will be intercepted closer to the station, giving you more time to get established outbound. Twist is changing the OBS to the outbound course of 275 degrees. Throttle is making the power reduction to the setting for approach speed. Talk is reporting to ATC as needed. If a report to ATC is not required, drop the last T. Remember to fly and navigate the airplane before talking. On the intercept heading of 320 degrees, wait until the CDI is halfway between a full-scale deflection and the center to turn to intercept the outbound course. As you fly outbound, don't chase the nav needle. At pilot, a half-scale deflection is about 3,200 feet, increasing to 8,250 feet at the 10-mile limit for the procedure turn. Always use a guesstimated wind correction. Hold the heading. If you let the heading wander, you won't know where to start bracketing. Bracketing can be thought of as the art of finding the heading that keeps you on course. Bracketing consists of splitting the difference between a heading that took you off course and a heading that brings you back to a course. Don't change the heading until you have at least a 1-dot deflection of the CDI. With at least a 1-dot deviation, turn to make the needle move toward the center. Close to the station, the heading change should not be more than 10 degrees. The new heading will do one of 3 things. It will bring the needle toward the center, stabilize the needle at 1 dot, or let the deviation increase at a slower rate. If the needle moves to the center, the heading to stay on course is between the original and the correction heading. Back on course, split the difference. Hold the new heading. If needed, the next correction should be half of the previous correction. If the new heading stabilizes the needle or lets it continue to move off course, another 10-degree heading change is called for. Analyze the effect of the new heading to figure the next heading. Close to the station, use 10-degree brackets. At extreme distances from the station, the brackets may be as much as 30 degrees. Pilot intersection, or 6.5 DME from Riverton, is the initial approach fix and is labeled IAF. Start timing over Pilot. Judging the distance outbound for the procedure turn is normally on the basis of estimated ground speed and time from Pilot. On this procedure, we're using DME, so we know exactly how far we've gone, but it's good practice to time it anyway. The procedure turn must be completed on the north side of the approach course and within 10 miles of Pilot. Within those limitations, it's entirely up to you where and how to make the procedure turn. Practically, you want to complete the turn far enough from Pilot to give you enough inbound tracking to get established on the approach course before the final segment, which starts at Pilot. The first turn of the procedure turn is mandated by the chart. On this approach, a right turn. Jeppesen charts depict the entire turn. FAA charts do not. An easy way to remember the direction of the second turn is that it's opposite the first turn. The procedure turn leg, 320 degrees, is flown as a heading with perhaps a guesstimated wind correction. Time starts when the turn is completed. Twist the OBS to the 95-degree inbound course. After 1 minute, make a left turn to 140 degrees to intercept the 95-degree inbound course. The minimum altitude until the procedure turn is completed is 7,700 feet. After you are established inbound on the approach course, you may descend to 7,400 feet. The pre-landing checklist should be completed by the time the airplane reaches Pilot. After crossing Pilot, which is the final approach fix, a descent to the MDA is made. This calls for a descent of 1,460 feet to 5,940 feet. The descent to MDA should be made as rapidly as practicable. The 5.7 miles from Pilot to the runway allows a somewhat lower descent rate than you may find on other approaches. Don't be reluctant to descend to the MDA. After crossing the final approach fix, obstacle clearance at the MDA is assured from the fix to the airport. Non-precision obstacle clearances are horizontal. They do not slope downward. Inbound from Pilot, check the missed approach instructions in terms of whether the initial climb is straight or in a turn. You should have the initial part of the missed approach in mind. Don't try to memorize the entire missed procedure, but do know the initial move. Virtually all missed approaches start with a climb, so know whether to turn or go straight in the climb. You can descend below 5,940 feet if the runway is in sight. The airplane is in a position from which a normal descent will bring it to the touchdown portion of the runway, and the flight visibility is at least 1 statute mile. That completes our look at VOR approaches and an examination of Jeppesen approach charts. We've talked briefly in this section about procedure turns, so coming up, we'll look closely at this maneuver.
Procedure turns are used to reverse direction and establish the aircraft inbound on an intermediate or final approach course. The altitude shown on the chart for a procedure turn is a minimum, and the maneuver must be completed within the distance shown on the chart. The distance is usually 10 miles, but may be 5 where only Category A airplanes and helicopters operate, or may be extended to 15 miles to accommodate high-performance aircraft. Both this distance and the side of the course on which the procedure turn are charted are critical because only by following the procedure are you assured of terrain and obstruction clearance. A procedure turn is a required maneuver except when the symbol no PT is shown, when the aircraft is being radar vectored for the approach, when conducting a timed approach, or when the procedure turn is not authorized. On the ILS to runway 10 at Millville Municipal Airport in New Jersey, for example, no procedure turn is required if you fly the transition shown from the Smyrna VORTAC. The most common procedure turn is the 45-degree type. Fly outbound, do a 45, a 180, and then intercept. Some pilots use an 80-degree, 260-degree course reversal instead of the 45. This is fine, just be sure it is done on the correct side of the outbound course. If the chart shows a procedural track, such as a teardrop, where you fly outbound on one radial and then turn and fly inbound on another, that procedure must be flown as charted if you do a procedure turn. Another example of a procedural track would be a DME arc. At Beeville Municipal in Texas, the DME arc is at 2,000 feet, 9 miles from the Three Rivers Vortac. Many of the procedure turns charted now appear as holding patterns at an intermediate fix or the final approach fix. The holding pattern maneuver is considered complete when the airplane is established inbound after the appropriate entry. If cleared for the approach while in a holding pattern, and if the aircraft is at the prescribed altitude, no additional circuits in the hold are required or expected. If it were to be necessary to fly another pattern to lose altitude, the controller should be informed. Where the aircraft is radar vectored or the chart specifies no PT, no pilot may make a procedure turn unless one is sought from and approved by air traffic control. In actual practice, procedure turns are rarely flown unless you happen to be flying to an airport where there is no radar coverage and there is no published transition from the direction of the aircraft's arrival. For example, if you are arriving at Frederick, Maryland from any point to the east or north, you'd likely be cleared over the Westminster VOR to fly the published transition. If coming from the south or west, you'd likely be cleared to the Frederick VOR and then for an ILS approach. As you can see, there is a published transition from the VOR to Rickey. From Rickey, you'd go out and fly that published procedure turn. How far you go beyond Rickey before starting the turn is at your discretion, but you must at all times remain within 10 miles of Rickey. One other word on procedure turns. It helps to know the approximate wind aloft, because if it's strong, you would want to apply some approximate drift correction in flying the procedure turn. You'd also want to be aware were the wind such that it might blow the airplane further than 10 miles away if the maneuver were started late. If your airplane is GPS equipped, you can see exactly how far away you are. Just make sure your navigator is displaying the distance to the correct fix or waypoint.
An ADF needle simply points to the station being tuned. Intercepting bearings to or from a non-directional beacon, an NDB, is a relatively simple matter of visualizing angles. Let's look at how this works on a procedure turn. After making the 180, the next thing to happen is an interception of the final approach course. Looking at the ILS to runway 5 at Shenandoah Valley Regional in Virginia, consider that you have just made a 180 on the procedure turn and are inbound to the final approach course on a heading of 90 degrees. That's 45 degrees off the final approach course. The ADF is tuned to the outer marker. The needle will be to the left. How far to the left will give information on the aircraft's position in relation to the final approach course. Because the heading is 45 degrees off the final approach course, the airplane will intercept when the ADF needle is 45 degrees off to the left. Before we intercept it, it will be less than 45 degrees off to the left, moving toward the 45-degree point. The closer the ADF gets to the 45 degrees off to the left, the closer the aircraft is to the localizer. If, because of a strong westerly wind, the aircraft blew through the localizer during the procedure turn, you'd see the ADF more than 45 degrees off to the left with the aircraft on a heading of 90 degrees. This covers the principle by which all interceptions are done. Know the difference between the heading of the aircraft and the desired bearing in degrees, and you know the number of degrees off the nose or tail of the aircraft that will be indicated on the ADF when the bearing is intercepted. Say that you are given a clearance to fly a heading of 225 degrees to intercept the 180-degree bearing from an NDB. Here you know that the ADF will be off to the right of the tail position more than 45 degrees before you intercept and 45 degrees off when you do intercept. If you fly through the bearing on that heading of 225, the ADF needle will be less than 45 degrees off. Inbound and outbound, you're looking for the same thing, an ADF deviation equal to the difference between the intercept heading and the track. Going away from the station, though, the needle will start farther from the tail and move toward it. Going toward the station, the needle will start closer to the nose and move away from it. If you wanted to fly to a station on a certain bearing, here's how that would work. Turn to the heading that corresponds with the bearing and note the deviation from the nose position on the ADF. For an example, let's say it is 20 degrees off to the right. Add 30 degrees to that and turn to the right 50 degrees. Right after the turn, the ADF needle will be 30 degrees to the left. Its deviation away from the nose position will increase, and when it is 50 degrees off to the left, you have intercepted the desired bearing to the station. To intercept an outbound bearing, determine the number of degrees the ADF is off the tail position when flying the heading that corresponds with the desired track. Say the ADF is 20 off to the left. Add 30 to the 20 and turn 50 degrees left. The difference in outbound is that the ADF will be 70 degrees left after the turn is made. When it gets back to 50, the bearing will have been intercepted. On some ADFs, you can set the heading of the aircraft at the top. Then the ADF will point to the present bearing to or from the station. On a fixed card ADF, you can add the magnetic heading to the relative bearing to calculate the course to the station. The reciprocal of that course is the bearing from the station. All the old hands, though, think in terms of intercept angles and needle deviation from the 180 point if intercepting a bearing and flying away from the station, or from the 0 point if intercepting and flying toward the station. Tracking the desired bearing with the ADF is an extension of all this. Let's say you want to track to the station on a bearing of 360 degrees. When that bearing is intercepted, turn to 360. The needle should be right on the nose of the airplane. If there is no wind or it is directly from 360 or 180, the airplane would go to the station on the desired track. There is almost always some crosswind, though, so we have to correct for drift if the airplane is to track to or from the station on a predetermined bearing. If after flying 360 for a few minutes the needle is off to the left 10 degrees, that means that the wind is from the left and the airplane has drifted off course to the right. The first task is to re-intercept. There are rules of thumb on the intercept angle that would be proper. Let's use 30 degrees. When we turn 30 degrees to the left to 330, the ADF needle goes where? If you thought 20 degrees off to the right, you thought correctly. Fly until it is 30 degrees off to the right and you'll be back on track. Leave in 10 degrees to the left for correction and fly 350. The ADF needle will be 10 degrees off to the right, and if this is the correct drift correction, it will remain there. If it doesn't remain 10 degrees to the right with the heading 10 to the left, then some refinement of the drift correction is needed. Intercept again and use either more or less drift correction as the case may be. Let's track outbound on 180. To begin, the needle stays right on the tail. Then the airplane drifts off to the left. The ADF needle will be 10 to the right of the tail position. When we make the right turn of 30 degrees, it will move farther off the tail to 40 degrees. That isn't how it worked when going toward the station, but the next step is the same. When the needle moves back to where it is 30 off the tail, the airplane is back on track. Fly a heading of 190 to allow 10 degrees of drift and see if the ADF needle remains 10 to the right of the tail position. Tracking outbound, both the ADF needle and the heading are to the right if the wind is from that direction. Inbound, the heading was to the left and the needle was to the right. Inbound, opposite sides. Outbound, the same side. Either way, to the station or from, the track that you make good will only be as accurate as your magnetic compass and the setting of the directional gyro with that compass. If your compass were 10 or 15 degrees off and you were flying toward a station, you'd get there, just not on the precise track. Tracking outbound, any compass error will result in you getting farther off the desired track the longer you fly. Some pilots, not liking the mental gymnastics associated with basic ADF interceptions and tracking, tend to only use their ADF to fly to a station with no wind correction. This is called homing, and instead of following a track to the station, you will fly an arc because of the wind. In a minute, we'll be showing you how NDB approaches work. For now, though, Dick Collins is going to tell us a bit more about the ADF.
In many years in the aviation magazine business, I wrote several articles about the ADF.
Every other aviation writer has done the same thing, and occasionally every one of us thinks that we have come across an absolutely magic way of explaining the ADF so that everyone can understand it. So we write yet another article. I guess I thought I had a leg up on some because at one point I worked for a school that was training U.S. Air Force cadets. This was a while back when the ADF was the primary means of navigating a lot of the airplanes in the Air Force. We spent endless hours teaching cadets and student officers how the ADF worked and all the things that you can do with the equipment. Some of them seemed to understand it. Some seemed to leave happy with the knowledge that if you keep the needle pointed straight ahead, the ADF will eventually lead you to the station. It was this experience that kept sending me back to a new and improved ADF article. Anyway, I don't remember when I wrote the last ADF piece, but when I did, Gordon Baxter kidded me about it. He said it was too technical or something to that effect. Okay, Gordon, you write an article about the ADF. He did. It was short and simple. Gordon's title was, "It's Over Yonder," it being the station. The little needle just always points to the station, telling you that it is over yonder.
So I quit writing magazine articles about the ADF. It sure is easier to show them in video with all these nice pictures.
Talk to enough instrument pilots, and you'll find at least one who will insist that an NDB approach is an emergency procedure. It's too bad that this procedure has gotten a bad name in some circles, because NDB approaches have a lot going for them. A non-directional radio beacon is relatively inexpensive. The site requirements are minimal, and before GPS, an NDB was often the only practical way to make the airport a part of the IFR system. There are two basic kinds of NDB approaches. The most common one is with the NDB located on the airport. This is also the simplest one to fly, as well as the one that will lead you most precisely to the airport. With the aircraft on final approach, the ADF needle simply points at the airport. What more could you ask? The other type NDB approach would be with the beacon away from the airport. At Belfast, Maine, the beacon is right on the airport, not far off the side of runway 1533. This one is a little unusual because it has a step-down fix based on a radial off the Bangor Vortac. The Boogie intersection could also be identified using an approach-approved GPS. Bangor Approach Control is in charge of the airspace, and they might well vector the aircraft to the final approach course. If that were the case, you would fly a simple intercept of the inbound bearing using the procedure discussed earlier. Let's say that the controller assigned a heading of 175 degrees to intercept the final approach course. That's about 30 degrees off the final approach course. So you'd fly that heading until the ADF needle was 30 degrees off to the left of the nose, at which time you would turn inbound on final. The controller would tell you how far you are from Boogie when you intercept. If within 10 miles, you could descend to 1,900 feet at that time. At Boogie, the descent to the 840-foot minimum descent altitude could be started. If for some reason Boogie could not be identified, then 1,900 feet would be as low as you could descend. Some NDB approaches do not have a step-down fix. On those, the descent to the MDA is begun as soon as the procedure turn is completed. Back to Belfast. If the approach were made without radar vectoring, there is a published transition from both Bangor and Augusta. In both cases, you would track the radial to Boogie, which would be identified by the bearing on the ADF and the 224 radial from Bangor. From Bangor, the ADF needle would be 80 degrees, plus or minus any wind correction, to the left of the nose on interception. From Augusta, the ADF needle would be 53 degrees, plus or minus any wind correction, to the right at Boogie. After reaching Boogie from Augusta, a left turn to a 279-degree heading will intercept the outbound course at a 45-degree angle. The ADF needle would be 45 degrees left of the tail when the outbound course is intercepted. From Bangor, a right turn to a 9-degree heading would intercept the outbound course when the ADF indicates a bearing of 45 degrees to the right of the tail. The outbound course intercept could be made at a 30-degree angle, but would be less accurate for determining when to start the procedure turn. The next step would be to fly the charted procedure turn and intercept the final approach course inbound. The simplicity of the ADF makes it easy from the time you intercept the final approach course inbound because the needle points to the airport. The track should be made good with any necessary correction for wind, but still, it's neat to have that ADF pointing to the airport. The NDB approach to Wiscasset, Maine is a good example of an approach where the beacon is not located on the airport. The critical part of such an approach is in tracking precisely away from the station on final. There are 3 published transitions if the approach is made without the benefit of radar vectoring. All 3 would require a procedure turn. The transition from Angkor looks like it could be a straight-in, but you would have no way of knowing by means acceptable to the FAA that you were within 10 miles of the NDB, so 1,900 feet would have to be maintained to the beacon. Careful setting of the directional gyro is mandatory on any NDB approach. Then, with the heading on 268 degrees, or whatever it had been for wind before passing the beacon, watch for any needle movement away from the tail position or from the amount of wind correction that had been used when flying toward the beacon. If the needle moves right, make a correction in that direction. Left calls for a left correction. Because the distance is short and hopefully you had a good correction for wind before passing the beacon, a correction of 15 degrees toward the needle should suffice to get quickly back on track. That would move the needle an additional 15 degrees off the tail. Heading, for example, 283 degrees for a correction to the right, the needle would be 15 degrees, 5 degrees to the right for wind correction. The turn would be to 288 degrees. That's 20 degrees off the track. So when re-intercepting, the ADF would be 20 degrees off the tail, and you might want to turn back to 278, which would be a 10-degree correction for wind. The ADF needle would be 10 to the right of the tail. The heading would be 10 degrees to the right of the desired outbound track. In all of this, we have ignored the possibility that the airplane might have an approach-approved GPS. If it does, there may be an overlay GPS approach, and then you can use the GPS to fly the NDB approach with a lot more precision. Even if your GPS is not approach-approved, or if you have LORAN-C or a VOR DME area navigation unit, it's foolish not to back up the ADF with the additional information available from another source. Holding may be encountered on any phase of an IFR flight. Some departure procedures call for climbing in a holding pattern. En route, you must hold if you've not been cleared to your destination and have reached your clearance limit. On arrival, many approach procedures use a holding pattern for the course reversal, and all missed approaches end up in a hold. Holding patterns are as charted, or as given by the controller. For a hold that is not charted, the controller will tell you what direction to hold, the holding fix, the bearing or airway upon which to hold, leg length if necessary, the turning direction if it is left, and the expect further clearance time. The end of the inbound leg is marked by the holding fix. This may be a navaid, waypoint, intersection, or DME distance. To begin, you fly to the holding fix. You should slow to holding speed at least 3 minutes before reaching this fix. Holding speed will vary by airplane, but it must not be faster than the maximum speeds published in the AIM for your altitude. Some holding patterns have different speed limits charted. The standard holding pattern uses right turns and a 1-minute inbound leg up through 14,000 feet, 1.5 minutes above 14,000 feet. Some holding patterns specify a DME or RNAV leg length instead of time. If you are holding at a VOR, start your outbound turn at the first complete reversal of the to-from indicator. Start timing the outbound leg when either above or abeam the fix, whichever is later. If you can't determine when you're abeam, start timing when the outbound turn is completed. At 14,000 feet and below, use 1 minute for the first outbound leg, and adjust the timing on the subsequent outbound legs to compensate for wind to make the inbound leg 1 minute. Turns should be standard rate, but not more than 30 degrees. If you're using a flight director, the maximum bank angle is 25 degrees. Except when turning, you should compensate for the wind. Outbound, you should triple the wind correction angle used to track the inbound course. This will distort the racetrack shape, but keep you inside the holding pattern protected airspace. The protected airspace is not charted, but it is shaped somewhat like and centered upon the holding pattern. This puts about 60% of the protected area on the holding side, so the majority of your maneuvering should be there. How much airspace is protected? The FAA uses 31 different templates for holding pattern protected airspace to fit over 100 combinations of altitude, fixed to nav-aid distance, and airspeed. The smallest size, used only up to 4,000 feet, is 6.7 nautical miles wide. Up at 46,000 feet, where the wind blows stronger and the jets fly faster, the FAA uses a pattern that is 57 miles wide. The miles of protected airspace are there to allow for dead reckoning on the holding pattern entry and on the outbound legs in a minimum 50-knot wind. This is not an excuse for sloppy flying in a holding pattern. Staying safe depends on compensating for the wind and following the recommended procedures. The FAA holding pattern entries are designed to transition you into the hold with a minimum of turning while keeping you in protected airspace. For the instrument knowledge test, you must know when to use the parallel, teardrop, and direct entries. On the flight test and in real life, you may use any method that keeps you in the protected airspace, and we'll cover some alternate entry methods in a minute. Flying toward the holding fix, look at where the outbound course falls on your heading indicator, or HSI. Divide the indicator into 3 segments, like so, for a standard right turn hold, and you can visualize exactly what kind of entry the FAA expects of you. Note that this visualization on the heading indicator is simply the FAA entry pattern diagram flipped and rotated so that the teardrop section is on the upper right. The teardrop section is the smallest, only 70 degrees on the right of the nose. At the fix, turn to a heading 30 degrees from the outbound course toward the holding side for 1 minute. Then, turn in the direction of the holding pattern to intercept the holding course. The direct entry section is the largest, covering a 180-degree arc. Simply turn right, outbound, and fly the pattern. The parallel segment is the 110 degrees to the left of the nose. Turn to the outbound heading, correct for wind if known, fly for 1 minute, and then turn toward the holding pattern more than 180 degrees. Return to the holding fix or intercept the holding course inbound. Note that a parallel entry is only truly parallel in a no-wind condition. Many pilots prefer the additional precision afforded by tracking the inbound course outbound instead of the FAA's dead reckoning parallel entry. A non-standard holding pattern uses left turns, and the entry procedure diagram has to be flipped so the teardrop section is in the upper left. A rule of thumb can help you visualize the entry needed. For non-standard left turns, use your left thumb to mark the 70-degree teardrop section, and the remaining sections fall into place. Right turns, right thumb. There are also devices available to help determine the correct entry. These diagrams can be difficult to visualize in the cockpit, so some instructors recommend simply flying a teardrop anytime you can't use a direct entry. An old Air Force method takes the opposite tack and suggests flying a parallel entry whenever the direct entry isn't possible. Both of these alternatives may involve a little extra turning, but they'll keep you in the protected airspace and minimize mental math. Circling approaches are approaches which either do not meet runway alignment criteria, or approaches which provide for landing on a runway other than the one aligned with the final approach course. The approach chart designates a straight-in landing runway if there is one. Landing on another runway requires circling, and different minimums apply. For a straight-in approach, the angle between the intersection of the extended center line of the runway and the final approach course cannot exceed 30 degrees, or 15 degrees for GPS approaches. A circling-only approach is either not aligned with a runway, or in the case of a few procedures, one where a straight-in would require an excessive descent on the final approach segment. The Localizer Bravo approach for the Eagle County Regional Airport in Colorado requires a descent of 6,965 feet from the final approach fix to the runway touchdown zone. It's 9.5 miles from the final fix to the runway. At a ground speed of 90 knots, this calls for a descent of 1,100 feet per minute. Because descent rates over 1,000 feet per minute on an instrument approach can be hazardous to your health, there are only circling minimums at this airport. At an airport which has straight-in minimums, a circling approach might be preferred if the straight-in runway is not usable because of wind or other reasons. Newton, Kansas City County Airport has several straight-in approaches and a VOR DME approach which is not straight-in. Approaches that do not have straight-in landing minimums are designated by a letter. This approach is designated VOR DME Alpha. The approach is classed as circling because the angle between the final approach course and the extended center line of the runway exceeds 30 degrees. On a circling approach, the charted approach procedure is flown until the airport or runway is in sight. One of the ground rules for a circling approach is that the pilot must maintain visual contact with the airport during the circling maneuver. Regulations state that a missed approach must be made if an identifiable part of the airport is not distinctly visible while circling at or above the MDA. The one exception is if a normal bank causes the inability to see the airport. Recall the ground rule for all approaches, that descent from MDA or DA cannot be made until the aircraft is in a position from which a descent to a landing can be made at a normal rate of descent using normal maneuvers. Aircraft approach categories are primarily established for circling approaches. The size of the circle flown is related to the speed of the aircraft squared. Twice the speed quadruples the radius of the turn. The obstacle clearance area for circling approaches is determined by connecting arcs, which extend from the center of the runway ends. MDAs for A category circling approaches are determined by arcs which extend 1 3/10 of a mile from the end of the runways. This distance is increased for each successive category. If you circle an aircraft at a speed higher than its category, you must use the minimums for the higher speed. For example, a Category A Skyhawk being maneuvered at 100 knots would have to use Category B approach minimums. Circling MDAs may be less than 400 feet and as high as 1,000 or more feet above the airport elevation. Circling an airport at an altitude of less than 400 feet AGL in a slow airplane in marginal weather conditions while concentrating on keeping the airport in sight can present a lot of problems. On this approach to Rock Springs, Wyoming, the Category A circling MDA is 7,120 feet, and the required flight visibility is 1 statute mile. At 7,120 feet MSL, the airplane will be 360 feet above the airport elevation. If weather conditions are such that the airplane is just below the clouds at 7,120 feet, and the visibility is 1 statute mile and it's dark, prudence would suggest landing straight in on runway 27. If the approach at Rock Springs seems like an extreme example, consider this approach. The Russell, Kansas VOR DME alpha minimum descent altitude for A category is 358 feet above the airport elevation. The airport has a beacon, and there are pilot-controlled medium-intensity runway lights and runway end identifier lights on runway 16. Flying this approach at minimums at night is not going to be a nice leisurely trip around the traffic pattern. All of the foregoing is to suggest that you have second thoughts before attempting each and every circling approach. Even the Russell, Kansas approach becomes less threatening if the ceiling is 800 feet or so and the visibility is several miles. If weather conditions allow, go ahead and fly the circling approach as high as pattern altitude. If the weather is good enough that you can make a normal straight-in approach and landing without unusual maneuvers or excessive descent rates, you may land straight in, even if the approach only has circling minimums. On a circling approach, you are expected to maneuver by the shortest path to the base or downwind leg. There is no restriction against flying over the airport or other runways. If the ceiling permits, fly over the airport to observe the wind direction indicators and look for other traffic. Some procedures have limitations on where you can circle due to terrain or obstructions. These will be noted in the procedure notes section on the top left of the chart. If a landing cannot be made, a missed approach must start at the missed approach point. The published missed approach or an alternate procedure specified in a clearance must be followed. If visual reference is lost while circling, the missed approach should start with a climbing turn toward the landing runway. The turn should be continued until established on the missed approach course. Have you ever looked at a runway in a dark area at night and wondered when to start descending? Were you concerned about wires and trees and wished there was a VASI? Landing from a non-precision approach at night takes a lot of care. There have been instances where airplanes have descended into unlighted ridges, trees, or wires while descending from the MDA with the runway in sight. Visual descent points, VDPs, have been added to many non-precision approaches. VDPs are a defined point on the final approach course from which, provided the runway is in sight, a normal descent from the MDA to the touchdown portion of the runway would be obstruction-free. VDPs are usually DME or GPS fixes, but could be any approved navigational fix. Approach charts show the VDP as a V on the profile view. No special technique other than identifying the VDP is required to use the visual descent point. Where there is a VDP, descent below the MDA should not be made before passing the VDP and having the runway in sight. Where there is a VASI, the VDP is positioned where the VASI slope intersects the lowest MDA. When you are at the VDP and at the MDA, you should also see on-approach slope indications from the VASI. The VDP is not a mandatory part of the procedure. If the aircraft is not equipped to identify the VDP, fly the approach as though the VDP isn't there. Don't confuse the VDP with the missed approach point. The missed approach point on a non-precision approach is not designed with any consideration as to where the aircraft must begin a descent to a safe landing. For example, the VDP on this localizer at Reno is 3.3 miles from the missed approach point. While the DME fixes used for VDPs are not mandatory, DME is often used on ILS, localizer, and VOR approaches to define required fixes. This ILS or localizer DME approach at Rock Springs, Wyoming, which doesn't have an outer marker, requires DME to identify HEBM, the 7.7 DME fix. The DME frequency is the UHF frequency paired with a localizer frequency, 109.3 MHz. Note the DME fix symbols indicate the IRKS DME fix. The localizer DME backcourse approach at Redding, California uses DME fixes off the Redding VOR DME instead of the localizer. The DME distance symbols show the VOR DME identifier, RDD. At Klamath Falls, Oregon, this approach to runway 14 uses the Klamath Falls VORTAC to define step-down fixes on the final approach segment as well as the missed approach point. Step-down fixes are defined points which allow descent to a lower altitude. They may be DME or any other navigational fix. Step down from 5,600 to 5,200 feet is authorized at the 5 DME fix, and at the 4 DME fix to the MDA of 4,680 feet. On some approaches, the step-down fix is optional. At Paynesville in Ohio, the approach has an optional step-down fix. If the 7 DME fix from the Chardon VOR DME is identified, the minimum descent altitude is 100 feet lower. Whenever DME is part of the approach, particularly on ILS and localizer approaches, you must be sure that you are using the right DME. It can be part of the ILS and the localizer frequency, or the DME distance can be from a nearby VORTAC. Be certain that you are using the correct DME. If you're using GPS, double-check that the distance shown is from the correct waypoint.
The TERPS manual provides vertical and lateral obstruction clearances for approach procedures and for airways. If you keep the needles centered and fly at the minimum altitudes, you'll always have the required obstruction clearance. In the next volume, we'll take a closer look at the TERPS manual and the margins provided for airways and instrument approaches. We've talked a lot about the details and the nitty-gritty of instrument approaches, but you really don't have to be a mathematician to be an instrument pilot. You should have some knowledge of what the navigational deviations mean in relation to distance to a station or to a runway. With a good notion of this, you can make more effective heading corrections. Far from the station, deviations call for larger heading corrections when flying with a system that gives angular deviation. Close to the station, smaller corrections are required. Knowing how much to correct is as important as knowing which way to correct. Too much of a good thing is as bad as not enough. Too much correction results in overshooting. Not enough correction, and the airplane never gets to the course. The straight part of straight and level is the foundation for good navigational tracking skills. If you let the heading wander, you won't have the foggiest notion of what heading it takes to stay on course. When you're able to hold a heading, tracking is simply remembering what the last heading did compared with what the present heading is doing. One of the most common causes for an approach to go awry is the pilot not being able to hold a heading and thus not being able to track properly. This seems especially true for NDB approaches. Some folks suggest that you shouldn't really even shoot an NDB approach unless the beacon's on the airport, or except right after training when it's still fresh in your mind. And I have watched pilots wander around a lot, flying a bunch of different headings and missing the airport by a lot of miles. In those cases, it would have probably been better if they had just flown the final approach course as a heading. They would have gotten closer. It takes practice, but it is worth learning to hold a heading and learning those tracking skills. Once you have those down pat, it's all a matter of keeping the pointed end forward and the dirty side down.
DME arcs are used to position airplanes on an approach course, or in rare cases, they are the final approach course. The arcs are limited to not less than 7 miles and may be 30 or more miles. As with all initial approach segments, obstacle clearance is at least 1,000 feet above the highest obstacle within 4 miles of the arc. DME arcs shown on approach charts look like a nice smooth portion of a circle. In theory, you could fly a nice circle if there was no wind and if you could maintain a constant, very shallow bank. Instead of a nice smooth circle, a DME arc is best described as flying a series of short, straight courses which approximate the distance from the vortex. Before we deal with how to fly the arc, let's break different size arcs into angular segments. A 10-degree segment of a 30 DME arc is 5.2 miles, and it goes all the way down to 1.2 miles on a 10-degree segment of a 7 DME arc. To fly an arc without extensive computations, break it up into segments which will take at least 1 minute and not more than 1.5 minutes. Depending on the speed of the airplane, the segments will be 10, 15, or 20 degrees. In no wind, at 120 knots, 10-degree segments on a 15 DME arc will take about 1 1/3 minutes. At the same speed, 20-degree segments on a 7 DME arc will take 1 minute and 13 seconds. Let's enter and fly the 14.7 DME arc for the Martin State Runway 15 approach in Baltimore, Maryland, starting at Slough, the initial approach fix. Inbound on a course of 155 degrees, lead the turn to intercept the arc. At speeds up to 150 knots, a half-mile lead is adequate. When the DME indicates 15.2, make a left turn to the heading that is at the 90-degree left index on the heading indicator. Since the inbound heading was 155, the first heading is 65 degrees. Set the OBS to intercept the 10-degree radial closest to the inbound course, in this example, the 340-degree radial. When the airplane is on this radial, check the DME. If the distance is 14.7, turn 10 degrees to the right. Less than 14.7, turn less than 10 degrees. More than 14.7, turn more than 10 degrees. How much to turn if the distance is not correct is a judgment call. As a rule of thumb, a half-mile or so off the arc calls for no turn if you are inside the arc and a 20-degree turn if outside the arc. Advance the OBS to the 350-degree radial, then make the same judgment call and turn 10 degrees to the right, less than 10 degrees if inside the arc, more than 10 degrees if outside the arc. Use step-down fixes, which are part of the approach instead of 10-degree segments. Continue the arc using step-down fixes or 10-degree segments. Having explained all this, you know why DME arcs are designed the way they are and the way the FAA wants you to understand them. In the real world, a perfectly acceptable DME arc can be flown once you're established by correcting 10 degrees every time the DME changes a half a mile. Wind makes any exacting formula you can compute in the air a bit of a moot point. Approach-approved GPS receivers can make flying DME arcs much easier with left-right course guidance along the arc. We'll go into the details of using GPS for approaches in Volume 6.
There's no way we can cover everything there is to know about approaches in one video. But what we do want to accomplish in any Sporties video, and what we have done, is giving you the best possible foundation for practicing and honing your skills. We've given you the tools you need to be safe and competent. And hopefully, we've given you the confidence to make safe and practical decisions as you fly. In Volume 4, we'll continue this process as we discuss the time that falls between departures and approaches, en route flying. So until we meet again in another Sporties video, I'm Rob Ryder. So long.